Hello everyone. Today we are releasing Ultra Scalable Ethereum on the Bankless newsletter. And if you want additional content to that, there is a paired State of the Nation where me and Ryan unpack this same content in a different format. But this was the piece of content that Ryan and I based that episode on. So here it is, Ultra Scalable Ethereum. Ethereum development is reaching a new level of maturation. The gap between where Ethereum currently stands and its defined roadmap is rapidly shrinking. Now that we're at this phase, it's become clear that Ethereum is developing a modular design architecture. The properties that make a blockchain are being differentiated and compartmentalized in order to allow each one to become individually maximized. In this article, we'll explore how proof of stake, sharding, and rollups enable a modular blockchain design that actualizes the long-term vision of Ethereum and sets the standards for blockchains going forward. The blockchain trilemma. The infamous blockchain trilemma dictates that you can only optimize for two of the three properties of a blockchain. One must be sacrificed due to technical limitations. Those three properties of a blockchain are scalability. How much data throughput does the system have? How many transactions per second? Decentralization. How many nodes are there? What are the centers of power? Security. How difficult is it to attack? So why is it the case? Why can't blockchains achieve sufficient decentralization, security, and scalability in one go? Because blockchains are monolithic. They try to achieve all three goals on the main chain. But when you modularize the components, however, the limitations of the blockchain trilemma disappear. As an analogy, think of the division of labor. This economic principle partitions a complex task into smaller components that individuals can specialize in, allowing the entire system to produce far more output than the same number of workers, each working alone. So what does a modular blockchain look like, and how does it work? Before we get there, we need to understand the three components of a blockchain that make up the three properties described above. Components of a blockchain. Decentralization, scalability, and security are all properties of a blockchain. They are traits a blockchain can embody, but there are underlying components that enable these properties. Modular blockchains divide these components into separate parts and maximize them. So what are they? Consensus. Consensus provides security and defines the canonical truth about data stored in the blockchain. What block number are we on? What are the contents on block number n? Execution. Execution is the computation required to update the blockchain from block n to block n+1, taking the old state, adding a bunch of transactions, and getting the transitions to a new state. Data availability. Data in the L1 data availability is data that the L1 guarantees is available to be referenced. All the data that makes up block n. Before diving deeper, let's get familiar and use these terms with an analogy. It's a Wednesday morning and you're heading to your local Wells Fargo branch office to deposit your check for $100. The state of your account is your bank balance, which is sitting at a healthy $69,420. All the previous account transactions from inception up until now are contained in the data availability layer of Wells Fargo, a centralized database hosted and secured by the company. When the bank teller processes your check, Wells Fargo executes a state transition against the data availability layer to update your balance to $69,520. The n+1 state, $69,520, is now reflected on your Wells Fargo mobile app, web app, and other branch locations. There is consensus because all updates take place on a centralized database that only people with the right credentials can access. Now, in blockchain terms, consensus. Consensus defines the canonical truth about data stored on the blockchain. In these categories, we find proof of work and proof of stake. These are the systems that define how blocks are added to the chain and how participants can agree that the blocks are correct. With this, blockchains can progress forward in time without fracturing into a million different chains, each with their own version of what is true. Execution. The execution property of a blockchain is where the state of a blockchain is carried forward into the next block. Block n has some specific state represented by how data has changed from block n-1, account balances, contract code, etc. Validators then grab a bunch of transactions from the mempool and create state updates to block n by producing block n+1, which has taken the state of block n and changed it according to the transactions that have been pulled from the mempool. The mempool is like a number of people waiting in line to go see the bank teller. Transactions are executed when a validator computes the new state of the next block using the selected mempool transactions as inputs along with the consensus mechanisms. Data availability. Data availability refers to the data hosted on each blockchain node. If there's data on the nodes, it's available to anyone and everyone using the blockchain. There are no dependencies on this data. It's available, full stop. This also makes data very precious and expensive. There's an extremely limited amount of this data available. We call it block space. When you add a bit of data to the blockchain, you're adding that data to all computers running the node now and forever. The purposes of a blockchain are to be immutable, which means that the data held inside of these systems are quite literally the most valuable kind of data ever created by humanity. Everyone wants their data, their transactions, to be immutable. So people bid very high prices to access these properties, which is why we see very high gas prices on the Ethereum L1. Monolithic blockchains. Monolithic blockchains are blockchains that try to do all three things: consensus, execution, and data availability, all in the same spot on the layer 1. Basically, every blockchain so far, including Ethereum as it currently stands, is a monolithic blockchain. The problem with monolithic blockchains is they are subject to the blockchain trilemma. Because the same layer is responsible for all three components of what makes a blockchain, optimizing for one property of a blockchain is constraining for the others. Want more block space available by making faster block times and bigger blocks? Then you have to decrease the number of nodes that can keep up with the chain's rate of progress. That way, the slow computers of the world won't hold back the speed of the chain. Want fast transactions? Reduce the number of nodes so fewer total computers actually need to do the computation. That way, we don't have a bunch of redundant computers all doing the same computation. We'll just trust that the few ones that do the hard work of the computation aren't lying to the network. Want to optimize for security and decentralization? Decrease the supply of block space and reduce your node hardware requirements so that everyone can be a participant in the network, but expect your transactions to take much longer to clear. Monolithic blockchains have gotten us this far, but now they are hitting the limits to scale. The era of monolithic blockchains is coming to an end. The era of modular blockchains is upon us. One sec. Modular blockchains. Modular blockchains take the three components that monolithic blockchains currently house on the L1 and compartmentalize them. Just like with the division of labor, unbundling each component allows us to optimize each and produce a far better product in which the whole is greater than the sum of the parts. Here's a nice little diagram. Modular execution with rollups. Rollups can process transactions orders of magnitude faster than the main chain. Rollups are unburdened from the responsibility of consensus and data availability by creating a transaction execution environment separate from Ethereum and processing the transactions before making an update to the state of the L1. Rollups do not have to concern themselves with consensus or data availability in the same way that highly decentralized L1s do. They are free to make any and all sacrifices on these properties because rollups are cryptographically tied to Ethereum. In other words, rollups are generated by making a transaction on Ethereum to a set of rules that the rollup commits to following. The moment a rollup is initialized, it makes a cryptographic promise to Ethereum that it will follow the rules. For the Harry Potter fans out there, it's like the unbreakable vow. You can't break it. If you break it, you die. You literally can't do it. That's what the power of cryptography does. This initial vow of rollups sets its own limitations on how transactions are managed, i.e., the rollup commits to showing mathematical proofs of all transactions are legitimate, and it's how Ethereum's L1 security is bridged to a rollup without also porting over its baggage of slow consensus and limited data availability. Contained inside this rollup initializing transaction is the ability for any user to exit all of their money from the rollup. This is called the escape hatch, and it means that when a rollup breaks or turns malicious, you can just hop out of the escape hatch via a transaction on the layer 1. A broken rollup is like a broken escalator. It just turns into stairs. The bridge between a rollup and Ethereum exists regardless of whether a rollup is online and functioning, and allows the settlement assurances of Ethereum to extend to the rollup on top of it. This bridge connects the security and decentralization of Ethereum to the transaction execution environment of the rollup. With this bridge, each module of Ethereum complements each other. The security module, proof of stake, is added to the scalability module, rollups. The properties of one module imbue themselves into the properties of the other, and it's how we achieve both scale and decentralization without compromising each other. Rollups cost nearly nothing to maintain. Sorry, one moment. Rollups cost nearly nothing to maintain, and very few nodes are required to be live at any given time. And they are also not burdened by expensive consensus mechanisms that are needed for security. Ethereum's L1 pays for security and maintains decentralization, so the rollups don't have to. Certain flavors of rollups can even be as performant as a centralized server. Hello, Coinbase, Fortnite, and Facebook, but now with decentralization. Further innovations to rollups can actually make them even more performant than centralized databases. Modular security with proof-of-stake validators. A proof-of-stake consensus mechanism creates an intangible object that is responsible for providing security to the system. That object is the virtual currency that is being staked to the proof-of-stake network. The act of using the native currency to validate the chain decouples the association between physical hardware and network security. No longer are specific computers responsible for network security. Now, all computers can become responsible for network security. Because ETH can be staked on any internet-connected computer, this formally instantiates the value of providing security to Ethereum into the asset itself. The capital requirement to maintain a physical proof-of-work network can instead be funneled into buying the virtual ASIC, the proof-of-stake token, and increasing the capital efficiency of the asset. Unlike physical hardware, proof-of-stake assets don't deteriorate over time, so little to none needs to be sold as operating expenses. Reducing the economic cost of running a validator node down to the cost of capital, 32 Ether, and a computer, the one you're on, increases the viable number of possible validators on a blockchain. While 32 Ether is expensive, roughly $128,000, it is an order of magnitude lower than the smallest viable proof-of-work mining operation, which is likely over tens of millions of dollars. Additionally, decentralized staking protocols like Lido or Rocket Pool allow ETH to become pooled, making the 32 ETH limit an arbitrary number. The yield you get from owning 3.2 ETH or 320 ETH is mostly the same and will approach parity over time. A proof-of-stake network strips away the hardware requirements for validating the chain, making the average consumer device powerful enough to validate the chain. This optimizes the connection between network and hardware. By minimizing the role of hardware, you maximize the accessibility of the chain and open up the possibility of validating the chain to the maximum number of people. Proof-of-stake minimizes the hardware requirements by down to the absolute minimum. Proof-of-stake minimizes the requirements of network validation down to the absolute minimum. Capital. As a result of proof-of-stake, Ethereum now has two homogeneous pools that, when combined together, become one modular pool of network security. This is called the validator pool and is where Ethereum sources its security from. Ethereum developers have stated a desire to see 10 million Ether staked to the Ethereum network in order for Ethereum to become considered secure. 10 million Ether divided by 32 ETH per validator generates 312,000 validators. The granularization of Ethereum security into individual validating instances allows these instances to be directed to the beacon chain, wherever these resources need to go. Allowed to be directed by the beacon chain to wherever these resources need to go, giving Ethereum maximum choice as to how to allocate its security resources. Having a modular pool of security enables Ethereum to modularize its data storage capacity via sharding. So here we go, sharding. Maximize data availability via sharding. Shards maximize the block space available on the L1. All blockchains have a certain supply of a security available to it. The security to Bitcoin is the supply of SHA-256 hashes that the world can produce. The security of proof-of-stake Ethereum is the supply of Ethereum validators that exists in the validator pool. Ethereum has a validator pool of all Ethereum validators that are set up for random selection to validate an Ethereum block. When more validators come in line and supply their security, 32 ETH, on the promise to follow the rules, to Ethereum, it makes Ethereum more secure. When you add in sharding, it will also make Ethereum more scalable. Sharding allow for a redistribution of security across a higher number of chains, rather than having all of the system security wholly pointed upon one single monolithic chain. Having 300,000 validators, 300,000 instances of 32 Ether staked, all securing one monolithic chain is an overabundance of security and an inefficient allocation of precious resources. By spreading out validators across multiple chains, Ethereum's L1 can scale by creating 64 Ethereums, each one having roughly 4,500 validators on each chain. This makes Ethereum scalability positively correlated with its security. While a monolithic blockchain approaches the limits determined by the blockchain trilemma, a sharded blockchain inverts the relationship between scale and security. It turns its limiting factors into its growth factors. Sharded Ethereum is slated to have 64 shards at the start, but the goal is to get up to 1,024 shards. Additionally, as Moore's law progresses and all of our household computers get more powerful, shards can increase in both quantity and capacity. Having 64 shards at Genesis won't mean that we're increasing Ethereum's capacity by 64x. Rather, the number of Ethereum chains will have gone up by 64 times. There will be literally 64 different blockchains, but the size of each chain will be roughly 1/3 as large as the current monolithic Ethereum chain. So overall, Ethereum gets about an 18x increase in size. But as stated above, as physical hardware improves and Ethereum's validator pool increases, we can increase both the size and supply of shards, which importantly links Ethereum scalability to Moore's law. So here's a little graphic I have of the beacon chain with its pool of validators, and the beacon chain is working on validating a block, so it sends all of the validators to each shard, kind of like, hey, line up in groups of 10, and then we have as many groups of 10 as possible, and then boom, that's as many shards as we have. This is not actually technically how it works, it's just a metaphor. All right, getting into synergies between optimized modules. The beauty of the modular design is that the optimizations of each module amplify the optimizations in the others. There are 3 synergies. Modular proof-of-stake security can redistribute validators across more shards as more validators come online and can securely support additional data. More decentralization means more scale. Additional shards on the L1 have amplified effects upon the execution capacity of rollups. Rollups can compress a lot of data before it adds it to an L1 shard. So any additional space that shards have outsized impacts upon this available space on rollups. More scale means faster execution. The more net transaction activity that happens on the rollups, the more total fees are paid for buying L1 block space. More total fees paid for block space increases the revenue paid to L1 validators. The more validators are paid, the larger the incentive there is to spin up additional validators. Adding more validators to the layer 1 adds more computational resources that can create more shards. More shards? Go back to step 2 and repeat. More scale, faster execution. By sharding Ethereum into 64 different data availability layers, we create much more space for rollups to deploy their bundles of transactions and their bundles of thousands and thousands of transactions. Sharding the L1 has outsized impacts to the scalability of rollups on the L2. Because rollups compress transactions into compact bundles, any increases of data on the L1 creates orders of magnitude more space on the L2. This is where Ethereum gets microtransaction capable. Sharded Ethereum is where the floodgates open for all rollups. Increasing the amount of block space that's available to consume creates massive fee reductions on the shards of the rollups on top of the shards. The compressed rollup transactions, think a zip file, now has much more supply of available block space. Rollups amortize their cost of their L1 transactions across all the users of the rollup. If it costs 1 ETH to deploy a big bundle of transactions to Ethereum, it will spread that 1 ETH cost over thousands of transactors in that bundle. When we have 64 times more shards to deploy transactions upon, the cost per transaction should drop by orders of magnitude, which also increases the number of total transactions that the cost of the rollups can be amortized over. Sorry. Once this occurs, rollups are free to stop constraining their own amount of available block space as they currently do and really let the engine rev. The combination of shards and rollups allows for computational resources to become assets to the network rather than liabilities. More computers of any computational power can always contribute their resources to the network and have those resources become effectively utilized, regardless of how much resources that computer has available to give. A computer can either be a rollup validator and help compress data to the L1, or can contribute its resources to the L1 validator pool and help spin up more shards. Adding your node to a monolithic blockchain adds another bottleneck to the network must get through. A monolithic blockchain cannot process more transactions than a single node can. Since all monolithic chain nodes process all transactions, adding your computer to the monolithic network simply adds just another computer that needs to keep up with the network. Economic sustainability. Modular Ethereum is an economically sustainable Ethereum. This is the industry of crypto economics, and we need to get our economics right in order to get in addition to our cryptography. In economics, Gresham's law is the monetary principle stating that bad money drives out good. When someone is presented with two different monies, they will save the one that retains its value and spend the one that is losing its value. With fiat currencies, we see people fleeing to the currency that is losing its value the least, which is the dollar. But now, in the world of sci-fi economics, aka crypto economics, we can dream bigger dreams than not just losing value. Instead, in the crypto world, we can ask what currency is going to grow the most in value rather than losing the most in value. Bitcoiners are very excited about BTC as the first hard cap money that is promised to retain its purchasing power by being immune to future issuance. Bitcoin promises to become more scarce as the economy grows around it. The same supply of Bitcoin, but inside of a bigger economy, equals comparatively more scarce BTC. Ethereans are excited about ETH and its ability to be burnt as a function of demand for the Ethereum network, and the possibility of becoming deflationary, as opposed to Bitcoin's disinflationary, as a result of burning more ETH than issuing via EIP 1559. A bigger economy equals a higher ETH burn rate, which creates an increasingly scarce ETH. Transaction fees equal monetary premium. Turning Gresham's law into crypto economic terms, networks need to collect more transaction fees than what is being issued to validators. Crypto economic networks pay their security providers via issuance and fees. Using fee revenue to pay for security displaces the amount of issuance that is required. The more fees a blockchain collects, the less it needs to inflate supply through issuance. Collect more, issue less. Herein lies the problem with scaling a monolithic blockchain. Many blockchains promise low fees and high throughput. By committing to this, they are simultaneously committing to never creating a meaningful fee market. If you want block space to be cheap, you must not rely on transaction fees to pay for security. Therefore, you must rely on issuance, which in Gresham terms would be called bad money. An excerpt from Polynaya's writing. Let's consider Polygon, Proof of Stake, and Solana. Polygon Proof of Stake is collecting roughly $50,000 a day in transaction fees, or roughly $18 million annualized. Meanwhile, it's distributing well over $400 million in inflationary rewards. That's an incredible net loss of 95%. As for Solana, it collected only $10,000 a day for the longest time, but with the speculative mania it has recently seen, it's seen a significant increase to $100,000 a day, or $36.5 million annualized. Solana is giving out an even more astounding $4 billion in inflationary rewards, leading to a net loss of 99.2%. This data is actually old. Since then, Solana has increased in price, and so it is now giving away $6 billion in inflationary rewards. So what, 99.5%? That means that it's giving away 99 of all the money that it is either giving away or taking in as revenue. It's giving away 99.5% of it, and it only takes in 0.5-ish% of revenue. So it's completely unsustainable. Way too much issuance, very, very little being collected. That is like a government just issuing a bunch of money and collecting almost nothing in taxes. It doesn't work. It's just unsustainable. As a thought experiment, Solana would need to do 154,000 transactions per second at the current transaction fee rate just to break even, which is totally impossible given current hardware and bandwidth. The bigger issue, though, is that those additional transactions don't come for free. They add greater bandwidth requirements, greater state bloat, and in general, higher system requirements still, which reduces the number of network participants that can actually come to secure Solana down to a very low number of people that actually have the hardware to run a node. So while all of this issuance is being given out, very few people are able to actually collect that issuance. The critical feature of economic sustainability is that it compounds in both directions. A constrained layer 1 establishes a strong fee market. By limiting the amount of available block space, you increase both decentralization by reducing the hardware requirements of participating nodes, and you increase fee revenue by limiting the supply of block space available. Scarce block space creates high fee revenue, which generates a high ETH burn rate, which makes ETH more scarce, making it more valuable. The more valuable a currency is, the less is needed to issue in order to achieve the same impact upon security. Therefore, security actually becomes cheaper to pay for when the value of the currency is high. Under a cheap security paradigm, you further reduce net new issuance because you are simply issuing less, and this further compounds the scarcity of the value of the asset. When Ether or any proof of stake asset becomes increasingly valuable, you don't have to issue as much of it to pay for validators because it's worth more. Going in the opposite direction, it all unwinds. Chains that advertise a cheap fee environment cannot collect any meaningful fee revenue, or else it would have fees. If you cannot collect fees, you must pay for security via issuance. If you pay for security via issuance, then the currency inflates and it leaks value over time. Over time, being an inflationary currency is simply adding supply to the currency and reducing its value on the secondary market. Reduced value means you must issue more to pay for security. Further issuance inflates supply and devalues the money and represents the beginning stages of an inflationary spiral. If your currency that you're using to pay for security becomes less valued because you're issuing it, you have to issue more in order to pay for the same amount of security. While bull market speculation can mask this effect for a while, there is no escaping economic law. Currencies that issue will not hold their value as much as currencies that burn, and these two paths will result in dramatically different futures. There is a direct correlation between the throughput of the L1 and the soundness of the money that powers it. If you juice up the throughput of your chain, you increase the inflation of the asset. Sadly, when you also increase the throughput of your chain, you reduce the ability for the average person to become a validator. This separates the community that surrounds the blockchain into two classes of citizens: the ones that have the means to validate the chains, and those are the ones that have the rights to seigniorage, the newly issued coin, and those that don't and can only purchase the seigniorage from the validators that sell it to them. Separating your ecosystem into two classes of citizens is bad news. Don't do that. Tying it all together. All right, here's where we sum everything up. Ethereum has a constrained layer 1 that optimizes for strong decentralization and efficient security. This block space constrained L1 creates an expensive fee market that adds monetary premium into ETH. Sharding increases available L1 block space as a function of the size of the Ethereum security. As Ethereum's pool of validators grows larger, the number of viable shards also goes up, making Ethereum more scalable as it grows in decentralization. Rollups create unconstrained execution environments that bundle up transactions and compress them into the tiniest possible packet of data. This unlocks new types of economic activity and allows a vibrant and cheap economy to flourish, increasing the net economic activity that settles on the L1. As more economic activity develops on the rollups fees drop as they are amortized across a wider set of participants. As more shards are added to Ethereum, and as shards become larger, rollup fees continue to lower as a function of Moore's law. Unlocking microtransaction viability increases the total amount of viable economic activity that can be supported, allowing net economic activity orders of magnitude more headroom to operate, which is all funneled down to the Ethereum L1 via a series of compressions and commitments across various layers, and all collapses to the competitive fee market on the L1, burning ETH as a function of total economic activity. The beauty of the modular design is that it optimizes to each module. The beauty of the modular design is that optimizations to each module amplifies the optimizations to the other. Increasing decentralization via proof of stake increases the number of shards added to Ethereum. More shards on the Ethereum L1 adds more magnitudes of more scale to the rollups on the L2. More scale-ups on rollup L2s unlock newly viable economic activity, which ultimately adds more collective fees paid to the rollups to the L1. More collective fees paid to the L1 increases the incentive to run a validator, making the pool of validators larger, allowing for more shards to be created. Repeat. Execution optimized monolithic blockchains. Every bull market, there comes a new cohort of chains that elect to sacrifice decentralization in order to optimize for the execution property of a blockchain. They increase the block size and constrain the nodes so that the exuberance of a bull market can find a home with cheap fees. In bull markets, Ethereum and Bitcoin become extremely congested because they have optimized for decentralization, which gives legitimacy to the chains that optimize for the opposing property, transaction execution. As discussed above, monolithic blockchains that optimize for execution have committed to a few shortcomings. They cannot collect meaningful fees and they have sacrificed decentralization. If this execution optimized monolithic blockchain instead rolls itself up as an L2 on a different L1 chain, it could actually become even more optimized for execution while not having to deal with the constraining factors of security and decentralization. The L1 asset no longer needs to be issued to pay for security, since security is derived from the L1. Eliminating the inflation from a supply schedule allows the smaller gas markets to have an outsized impact upon the long-term supply of the native asset. Chains like Solana, Binance Smart Chain, Avalanche, and Polygon all may need to roll themselves up in order to derive long-term sustainability into their token. And in fact, the sooner they roll themselves up, the scarcer their native asset can become. From the words of Polynia, I used to think that this is the most pragmatic approach, but now I think there's too much capital and hubris invested in monolithic projects for them to take this roll-up only approach anytime soon. The one that does will be a pioneer and gain immense network effects, though. The logical conclusion. The world of crypto is rife with tribalism and politics. Statements uttered by one person in crypto is tainted by which tribe that person comes from. Incentives and motivations are driven by pre-existing beliefs and back bias. Thankfully, code and math are immune from all these things. The entire above article is able to be rewritten without using the word Ethereum, and instead could be an agnostic roadmap for a generally optimized modular blockchain. In fact, this architecture is not being executed by Ethereum alone. Rollups are not just an Ethereum thing. Tezos is also embracing a rollup-centric roadmap. Near is also designing for sharded data availability. Celestia is building a security and data availability layer exclusively for rollups. The point is, if we went back in time or hopped to a different parallel universe and re-rolled the dice 10,000 times, the crypto industry would find itself at a modular design conclusion 99.9% of the time. It is simply the logical conclusion of the development of the blockchain industry. And it is the only reason why it has been politically linked to Ethereum is because Ethereum has been the only ecosystem to adequately fund R&D efforts that have been able to bring us to this point. Over time, we will see all L1 blockchains either morph into a modular design structure by constraining the L1 block space, pushing execution to rollups, and increasing the node count, and compete in the world of global non-sovereign money, or they will instead do away with the baggage of consensus and data and simply port their execution environment over to a more decentralized chain. The modular blockchain design also illustrates the necessity of enshrining decentralization as the key property of blockchains that enable all the rest of the features. Ethereum has solved for the scalability trilemma by increasing decentralization, not sacrificing it. Only by optimizing for decentralization are you able to receive the benefits of modularization illustrated above. If you have decentralization, you can have anything. Thank you for taking the time and listening to this, and I hope you guys all understand modular blockchains a little bit better today. It is going to be a concept that we continue to explore on Bankless, and I think the rest of the crypto industry as well. So cheers. Thank you for tuning in. Have a good day.